be a non-zero vector. So that's something that people neglected to observe. Okay. So,
are we just missing a statement in there about P, assuming P is a or let P be some non-zero?
well, for the statement you need is, I put in, very carefully put in the problem that P is not a zero matrix.
Right.
Yeah.
So if P is not a zero matrix, then there is some vector that you can multiply P by and get a non-zero vector. Okay. So you need to use the fact that there is a non-zero vector PV. If the vector PV is non-zero, then this has to be true. Now it's true you can't divide by a matrix, but for each component, right, you get an equation for each component. Like the first component here is lambda times the first component here. As long as I have a component that's not zero, then I can divide by that component. So you need to ensure, so let's just do this. So you need to ensure that PV is not the zero vector. All right, one more homework problem, and let me see if I can get Christy back on. Oh, it's going to take a little while, so she'll just have to miss something. Maybe you guys can. Well, I'll have this on on OneNote so she can read that.
Dr. Tom.
Yes. Was that?
Yeah.
Oh, you're recording. Okay, very good.
Yeah.
Okay, thank you. I hope that will that pick up the sound too?
I hope so.
Okay. All right. All right. Well, we'll give it a shot. Okay. And thank you. That's very helpful. All right, so let me look at problem 8, which a lot of people went through great contortions to do this. And just want to see if we can do it a little bit more simply. Now, where'd it go? Okay, here we go. Oh, we'll do 8C. So this is one of those things that you can plunge ahead and do it the direct way, or you can try to figure some way to organize it. Okay, so here it says, it's in a 4 by 4 diagonal matrix D with diagonal entries A, B, C, D. Find the characteristic polynomial PD and evaluate PD and D. Okay, so here we have D is equal to A, B, C. And the characteristic polynomial of D is going to be the determinant characteristic polynomial is equal to the determinant of what? What do you do?
D minus lambda.
You take D minus lambda, so let's just, so what's that going to do to D?
Just minus lambda across
Yeah.
the
A
diagonal.
minus lambda, B minus lambda, C minus lambda. And in fact, you know what that is. How do you take the determinant of a diagonal matrix?
Multiply across.
You multiply all the diagonal entries. So that's equal to A minus lambda times B minus lambda times C minus lambda times D minus lambda. Now, what the problem asks you to do is evaluate PD of D. So that means you take that expression and replace it with D. This was PD of lambda. So PD of D means you take lambda and replace it by D. You guys had a lot of fun with this. So PD of D is equal to A minus D times B minus D times C minus D times D minus D. And I put some spaces there because just like with when you took lambda minus when you take the eigenvalue, you take lambda minus the matrix. Really what this means is A times the identity minus D, B times the identity minus D, C times the identity minus D, and D times the identity minus D. You can't really take a number and subtract the matrix. You have to take a number times the identity matrix. So that's a I. Very egotistical equation. What's a I?
So we can recognize simplest form.
Sorry?
We could have left it in simplest
You could have left it in this form.
form.
Why not? Why not?
Because you usually find the short one.
Well, I am showing my work. Doesn't mean you have to do it hard.
I didn't know that answer.
3 pages later.
All right, now.
It only took me 1 page.
All right, but we're not done, right? We're not done. I wanted to show that this is 0. How are we going to show that this is 0?
Math it out.
All right, but you math it out, but you can do this a little bit more. Yeah. Okay, well, let's look at each term one by one.
Can you factor out I minus D from all of them?
No, you can't.
We'll just,
What is AI minus D?
A is down the diagonal minus.
Oh, wait a minute.
All right, now, when AI is A, and then it's minus A, B, C, D. So the first one is 0. I don't care about the other ones. First one is 0. So this is 0, and then I'll put star, star, star. I don't care about that, and this is 0 down here, 0 here. Second one, what about that?
Star, 0, star, star.
Star, 0, star, star. And then these are 0 here. And then star, star, 0, star. 0, 0.
Yep.
And then you have
Because you slowly.
star, star, star,
Well,
0, 0, 0. Now, what
because
happens
D-
when you
because
multiply
D-
diagonal matrices?
If you have A 0 down the diagonal.
Ends up turning to 0.
Well, let me just
Because
answer.
the zeros.
You need to answer that question in general. If I multiply 2 diagonal matrices,
You're just multiplying these
The
individual
diagonals.
elements.
you
on
just
diagonal.
multiply the diagonal elements,
You
right?
might have a 0 each side
So-
of the diagonal.
And eventually that zeroes everything out. That was too easy. I did that.
Oh, we all
No, you all did.
We all did.
I think we all did.
But, I mean, this is not, I mean, it's tricky. I think that this, where you put the i's in there, that's something that you might not think about. But remember, we did the same thing when we found the eigenvalues, right? We did the very same thing.
Thought about it, I wrote it all out.
Okay. But this is writing it all out.
It's just all written.
So if I have, say if I take D1 through Dn here, the zeros here, and then I say like F1 through Fn, and zeros here, it's going to be equal to D1 F1 Dn. So I mean, just think about how you would write this in a way so that each diagonal entry of the product is 0 because there's always one factor that has 0 in that place in the diagonal because the corresponding entry of one of the factors. So hopefully this can kind of sharpen up your thinking about kind of problem. So are we okay with that? Can we move on to chapter 13? All right, now chapter 13, I always think of bankruptcy, so this is the bankrupt chapter. Now, there's really there's really three ideas in this chapter. One is just general change of basis. Another is diagonalizability. And another is linear transformation, changing linear transformations under change of basis. So those are really the three ideas. What does change of basis mean? What does diagonalizability mean in terms of change of basis? And then what's a general change of basis due to a general linear transformation? And I really like these pictures. And I hope that you can relate to these. All right, I changed this one. Great. First important point here. So I tried to explain here. Whoops, we can zoom out. I tried to make the point here that different bases are basically looking at the same thing from a different point of view, from a different frame of reference. Now, the E1, E2, that's your usual frame of reference. But some weird smushed person might, instead of using E1, E2, might use V1, V2 instead. So I can express this vector x as a combination of E1, E2 or of E1, E2. And I can say, well, this is the right way to do it. And the smush guy says, no, this is the right way to do it. We can argue and have a theological discussion. And, but it's not just true for x, but for any vector. So first question is, if I know, given his point of view, can I figure out my point of view? How do you translate between points of view? If I know this, then how will I arrive at this? And the answer is, you can watch the video, and I think it says so right here. All right, yes, all right, so I did the other way. Sorry, I did the other way. Suppose I know his way. Suppose I know what he thinks. This is what he thinks, A and B. So what's the real way of doing it? What's the standard way of doing it? Now, in this part of the discussion, this one has to be the standard basis. So it's converting from another basis to the standard basis. And the answer is, I get from here to here by a matrix, and that matrix is exactly his vectors. If I know his vectors, and I know how he expresses this vector in terms of those vectors, I can take his vector, multiply by the matrix consisting of column vectors from his basis, and that will give me my way. So that's change of basis. Basic idea of change of basis when this basis is the standard basis. Okay. Now, how do you change back? Well, back just means inverse. I think I have that down here. So changing back just means so that's what I have here. Changing back from my way to his way, I just take P inverse. All right, so I wrote it this way. Now what I said is that, okay, let's introduce a linear transformation. Let's introduce a linear transformation over here. So he's looking at a linear transformation. And his linear transformation is diagonal. So the linear transformation looks very simple from his point of view. And how about from my point of view? What does it look like? So you follow this through. This is called a commutative diagram, and it's so prevalent in mathematics. If you look at our abstract algebra book, you'll find the same diagram. So very prevalent in mathematics. And the upshot is, so here, so I changed from my basis to his basis multiplied by p inverse. He goes, his linear transformation is diagonal, and then he can go this way. But I want to start here and go to here. Okay. So when I was flying home week before Thanksgiving, I was sitting in the Austin airport, and they said, we overbooked the flight. We have volunteers. Ends up I got a $2,000 voucher. Instead of direct flight to Boston, I took this flight. But I still got to Boston. Okay. All right, so that was quite incredible.
Yeah.
So my lesson is always fly direct to Boston on Thanksgiving and make a lot of money. In fact, they made the same offer in Atlanta for $500, and I missed it, so I should have been on the ball. And then coming back, they made another offer for $500, and I missed that one too. That's neither here nor there. So anyway, so if you haven't learned anything else, that's how you can make some money. All right, but see, if I go this way, I get the same place, right? So I multiply first by p inverse, then by d, then by t. And then the tricky thing is that when you're multiplying by these things, you have to go in reverse order, because you're multiplying the vector. If I take a column vector here, and I multiply by p inverse, I multiply by p inverse on the left. And then I multiply that on the left by d, and then I multiply that on the left by t. So the upshot is that my matrix is PDP inverse. Now, what is this P?
The column.
Those were these column vectors. Now, this is diagonal, right? That means that these column vectors are eigenvectors. You have if the matrix is diagonal, that means that any vector here, that a standard, then say, if this matrix is diagonal, I have the vector 1, 0, 0, 0 here. I multiply that by this, I'm going to get the first entry, and then 0, 0, 0, 0. Okay, so if these are eigenvectors, this is diagonal. So that's what diagonalization means. First, I find the eigenvectors. Then I form this matrix P from those eigenvectors. I find the corresponding eigenvalues, that's what the D is going to be. And then I can express M this way. So I think that's a much simpler picture than he has all these summation notation garbage stuff that really you can't see what's going on. It's really very simple idea. Well, it's simple once you get used to it.
And if you don't do problem number 4 on the web work, it can't be diagonal.
You may have to deal with that.
All right. So, all right, so we have that. So let me review this one also. All right, so that was a special case. Now let's do something more general. In fact, he does the more general thing first, which I think is kind of confusing. And then, so I did this with a simple example. So, suppose here I have two bases. And so just like I said before, you can express any vector in terms of either basis. And now this is a more general question. Previously I said I have a basis V and my standard basis E. How do I change back and forth between those two? This is a more general question. Suppose I have two different screwy bases. How do I go back and forth between these two? Now I'll just say what you do, so I can say this, I can actually put it over here. What you're actually doing is if I know that in the V basis, and I want to get to the V prime basis, well, I know how to get from the V basis to the E basis, and then I know how to get from the E basis to the V prime basis. I can do it that way. If I want to get from the V basis to the V prime basis, that's all I need to do. And essentially that's what I'm doing in this argument. I'm doing this same kind of commutative thing. I can't go direct, so I'm going around to Atlanta instead.
You get paid $2,000.
Well, you get paid with the A for the course, which is probably more than $2,000. All right, so here's my, so my x, so x is AB in the V basis. That means that x is this linear combination. If x is this linear combination, that means x is this linear combination. So x is AB times this vector. This vector consists of the two basis vectors of V. On the other hand, in this V prime basis, x is CD, but same thing, C times V1 prime plus D times V2 prime. So that means that x in the standard basis can be expressed this way. So this is two different ways of getting x in the standard basis. So I set them equal. And what that will allow me to do is translate from AB to CD. If I set them equal and I solve for CD in terms of AB, then I'm done. Okay? So that's what I got here. So I just solved it, and that's what I got. So I think so I just called that combined matrix P. But remember that P is actually obtained both from the V basis and the V prime basis. You take the inverse of the V prime matrix and then multiply that by the V matrix. And that will get you this P. So, what I did previously with diagonalization was introduce a linear transformation. And previously I said that the linear transformation is diagonal. Now I don't care, now I'm just going to say just general. Let me just take a general linear transformation expressed in terms of this basis in the domain and another basis in the codomain. So there are four bases floating around in this problem. There's the linear transformation expressed from V basis to W basis, and there's the same linear transformation expressed from V prime basis to W prime basis. You always express linear transformation in terms of bases. That's what makes the linear transformation a matrix. Okay. So if I go from V basis to W basis, I'm going to get a matrix here. Okay. I'm calling my linear transformation L. And the linear transformation L, if I view that in terms of V basis in the domain and W basis in the codomain, I'm going to get a matrix L. But I've got Joe over here who doesn't like my basis. He's got his basis. This is the Republican basis. This is the Democrat basis. So one basis for the domain, one basis for the codomain. So how can I know what Joe's matrix is from my matrix? Well, you can see I'm going to do the same thing I did before. It's the very same thing. I'm just going to complete the picture. To go from, well, you can see what's going to happen. To go from W basis to W prime basis, there's going to be some matrix similar. I'll call it Q, to go from here to here. And you make that a similar way. You take these vectors, take the inverse, and multiply by these vectors, get a transformation matrix here. And then there's just one side that's not complete. The one side that's not complete, well, I go to Atlanta again. So if I want to go from here to here, I have to go backwards on P, and that's P inverse. Then I go forward here, M, and here's forward on Q. And I do that from right to left. So it's going to be Q, M, P inverse. So I recommend when you do these problems, just draw a diagram. Don't just quote the formula. Draw a diagram and see what you're doing. And that's really basically all the ideas in this section. So let's consider some problems. I'll tell you what the problems are going to be. I can write it down here. So these are the end of chapter problems, and we'll do some of these in class. You have the web work also, but we can do some of these in class. So it's going to be 1, 2, 4, 5, and 7.1. Let me make sure about 7.1. I'm not sure what that is.
When are those gonna be due?
That will be due next Wednesday. Isn't that what I usually do?
Yep.
But we'll do some of them in class today.
Can you look at number 4 on the web works for us, and, because all of us are having trouble.
All right. Well, the apparently it's a buggy problem.
Okay.
It's a buggy problem. I thought that you need to put integers in the space, but even that doesn't work.
Yeah, it already has.
Yeah, it already has the integers there. I work it out and you just get a 0. You get one of your eigenvector to be all zeros. So
Yeah.
you can't take the determinant. Or
Okay.
the determinant is 0.
All right. Well, see, the thing is that might just be for you because it generates different numbers for everybody.
Well, mine ends up with a singular matrix too.
Oh, single matrix
Yeah.
too. Okay.
So,
All right. Well, Amanda's gonna send me an email, so I'll just.
I already did.
Okay.
matter of fact, now when on mine, it actually, after I worked it for an hour and figured out what was wrong, that I noticed that the